Hello, my name is Ralph Attard. I am a Microsoft certified trainer, and as an architect, I focus on software and data platforms. Today, I will be presenting the session on scaling databases using partitioned views. During the first part of the session, I will be introducing the need for scaling databases, and then we'll proceed to the second section that focuses on partitioning strategies, mainly vertical and horizontal partitioning. We will therefore look into triggers and updatable views, and then scale these further in the third section by focusing on distributed partitioned views using linked servers. The last section will shed light on database sharding, how this differs from distributed partitioned views, and the required application changes. Scaling databases. As software developers, database administrators, or system engineers, we usually inherit monolith applications, a single deployable artifact that uses only one database. As usage grows, the application environment starts facing performance issues. Increased data volumes and workloads leads to slower response times. We might be lucky that the application server is our bottleneck, and that the database server is at ease. In this case, our admin colleagues can load balance the application. However, we will eventually hit issues at the database level, and well-written indexes are not enough. We need to look into database scaling options. As our database grows, our queries become slower, possibly giving timeouts under heavy load. Backups become slower to take, to ship offsite, and to restore in case of disaster recovery. Performing index maintenance impacts production workloads even more. We have a number of options to optimize our database. We can start by scaling up vertically. We can maximize the hardware resources we have available on the server by adding more disk, more memory, more CPU. Or even we can migrate the database to a bigger server. We can also introduce read scaling. We can bring up a second server that replicates from the current database server and use it for read-only purposes. So we can split our queries between a read server and a write server. We can also restructure the database by improving the table design. We can also introduce aggregation tables to minimize the impact of running reports on production. And we can also offload data. We can archive all data. We can delete the extra data that we don't need. And we can also start reporting from a data warehouse instead from a production database. Simply adding more resources to a machine might not be enough. We need to scale the database from within itself. We can use vertical and horizontal partitioning to do this so that we can split the data across multiple tables, or even use the SQL Server 2005 feature of partitioned tables to split a table across multiple file groups and therefore multiple data files. We can then apply horizontal partitioning across multiple servers and introduce distributed partition views to consolidate these partitions together. We can also use database sharding to shift the consolidation to the application level by introducing routing to connect to the appropriate shard directly. Partitioning brings a number of benefits. The first benefit is that of scalability. Scaling up will eventually reach the physical hardware limit and we cannot scale further. Performance is also another benefit because smaller partitions are more performant and we can also query multiple partitions in parallel. From an availability point of view, partitioning reduces single point of failures because our data is split across multiple databases, multiple drives, multiple servers. Security is also another benefit. Sensitive data can be separated from non-sensitive data into different partitions and secured on its own. Our day-to-day administration is also more flexible by monitoring backing up, and performing index maintenance on a per partition basis. Partitioning strategies. Before introducing vertical and horizontal scaling, I wanted to mention a different partitioning approach. We can partition our data by domain. We might have white tables that are covering a broader domain that can be split into smaller tables, more fine-grained domains. These tables are usually grouped in a schema. For example, the HR schema, the production schema, the sales schema. Each of these schemas can be moved into their own database. The problem with moving schemas to their own database include issues with reports. Reports that are usually reading data from one database now need to mesh data together from different databases. We could also introduce a data warehouse to consolidate these different production data sources into one appropriately for reports. Although this approach to break the database down into smaller databases helps ease performance limitations or hardware limitations, each own smaller database can become a problem on its own. So this first strategy, the vertical partitioning strategy, looks into taking a table and split the columns into multiple tables. So for example, here we have a product table. We have the product ID, the name of the product, the price, and date created. Then we also have stock and last ordered date. This example splits this table into two and moves stock and last ordered date to its own table. So now we have two tables. Technically, they are two different data domains because one is product information and the other one is stock information. And we end up querying the table that we really need. Although we can still join these two tables together to get the original dataset as a whole. The second partitioning strategy is that of horizontal partitioning. This strategy sees multiple copies of the same table structure. So here we have the products table and we copy it to have two tables instead, products 2018 and products 2019. The difference is that data will be stored in the appropriate table by date created. So in this case, the products 2018 has products created in 2018, whilst that of 2019 will have those created in 19. Once we split a table into smaller tables, we have a problem with the application. The application doesn't know about these smaller tables. So if it is an in-house application, we can ask our developers to read from multiple tables. However, if this is not an option, we need to use views to transparently consolidate all these smaller tables as though as they are one big table, so that the application can still query this big view to access all available information. The problem with views is that not all views are updatable. We have two set operators that we can use to consolidate partitions together. If we applied vertical partitioning, we need to use a join operator. If we applied horizontal partitioning, we need to use a union. Although we usually create views to provide a consolidated set across all of our partitions, if we create monthly partitions for our transaction tables, this might become cumbersome and problematic because it is a repetitive task that needs to happen either at the end of each month or beginning of each month, and if skipped or done too late, it will provide less information than we actually have. So we usually end up creating a custom script or a stored procedure that is ran at the end of each month to dynamically create these views. Partitioned views have some requirements and performance implications. Each partition table that is created needs to have a check constraint, and the partitioned view needs to be using the union all operator. Also, querying the partitioned view without specifying the partitioning key in its predicate indirectly accesses all the partitions used in the view, as shown in the execution plan on the right. If, however, we filter by the partitioning key, it is only the specific partition that is accessed and thus apply a performance boost. As mentioned earlier, not all views are updatable. Below is a list of requirements for updatable views, such as modifications need to reference only columns in one table. This is important when you have a view which is joining multiple tables together. We can only update columns that are used in the tables. We cannot update columns that are a result of a group by, a having, or a distinct. We cannot use the top operator either. When our view is not updatable, we can use, instead of triggers, to write custom code that actually updates the underlying tables according to our business logic. Let's have a look at the first demo. So, for the first example, I'm going to create a new database named triggersdb, and we're going to look into the vertical partitioning. So we're going to have a list of countries and cities. We're going to store the countries in a table called country with a country ID and country name, and a table for cities with city ID and city name, but also the country ID, which is the foreign key to the other table. I'm populating it with two countries, UK and Malta, and inserting also four cities, London and Manchester for UK, and Valletta and Mdina for Malta. Now we're going to create the vertical partitioned view. Basically, we have an inner join between the country and city tables based on the country ID column. Once we select from the view, which is dbo.location, now we can see the list of countries and cities. So the first statement that I'm going to execute is an insertion. So I'm going to try to insert a new city named Glasgow for United Kingdom. As soon as I execute this statement, we receive this error. View or function dbo.location is not updatable because the modification affects multiple base tables. And therefore, I am going to create a trigger. This one is going to be instead of insert and instead of update. So basically, I'm creating this trigger to allow us to do whatever insert and update we want against both tables at the same time. The first update statement that we have here is to update the name of the countries by country ID. And the second one is to insert new countries. The third one is to update existing city names by city ID. And the last statement, the fourth one, is to insert new cities. So basically, for updates, On existing records, we're using inner join. And for inserts of new records, we're using left outer join with the inserted special table where there is no record on the right hand side. So once we execute this trigger, we should be able to insert a new city. There it is. So if I select, now we have Glasgow under United Kingdom. The next statement is a strange one because I'm doing an insert into the view, the view location, but I am changing United Kingdom to United Kingdom 2 for country ID 1 and Glasgow to Glasgow 2 for city ID 5. But if we do the select, we see that the country was updated to 2 and the city was updated to 2. So technically we are doing a multi-table update using an insert statement. And now we're going to add a new city, Oxford, to United Kingdom as well. So now we have the new city, Oxford, but since we used United Kingdom, not United Kingdom 2, the country name got updated as well. We can also insert a new country with a new city, and now we have Italy and Rome. Just for demo purposes, this trigger works well for updates as well. So I'm going to update the bo.location, change city name from Glasgow to Glasgow for city ID 5. And if I do that, now it is Glasgow, not Glasgow 2. The next example is for horizontal partitioning. So now we are going to split by rows instead of columns. I am creating two tables, one named employee and the other one named student. These tables are almost identical. All of them have first name, last name, date of birth, and email. However, employee has employee ID and student has student ID. So I'm inserting Joe Doe as an employee. I'm inserting Jane Doe as a student. And then I'm creating a new view, the bo.person. It's going to use a union. And I'm also adding an extra column, person type, to identify whether the person is an employee or a student, and also changing the primary key to a generic column name. So I have employee ID as person ID and student ID as person ID as well. Now that I select from the bo.person, which is the view, we have employee ID 1, person 1 as Joe, and student person ID 1 as Jane. If I try to insert a new student, Jane 2, it fails. Update or insert of view or function the bo person failed because it contains a derived or constant field. So now I'm going to create another trigger. This time it's going to be only for instead of insert, only for inserts. And basically I'm going to insert into the bo.employee the records from the inserted special table where person type equals employee, and insert the records in student if person type is student. So now I'm going to insert two records. I'm going to insert employee ID2 as Joe2, and student as ID2 Jane2. And if I select from both source tables, employee and student, we're going to see that we have Joe2 and Jane2. So basically this trigger inserted records in multiple tables from a view. The next example that I have is with regards to updatable views. I'm going to create a new database named viewsdb, and in this database I'm going to create three tables: person 1, person 2, person 3. I'm going to have basically a partitioning key column named instance, which is numeric. Then we have the person ID, first name, last name, and a primary key between the partitioning key and the ID of the records that we want. Now I'm also creating a view which unions the columns from person 1, person 2, person 3. And I'm going to make an insert. I'm going to insert a record in the person table. It gave me an error: update or insert of view or function dbo.person failed because it contains a derived or constant field. So that's the first attempt. Now I'm going to change it from union to union all. And I'm going to insert again. And now I have another error. Union all view viewsdb.dbo.person is not updatable because a partitioning column was not found. We need to introduce a partitioning column. We do that by using the check constraint specifying the column, which is instance, and going to specify person 1 for instance 1, person 2 table for 2, person 3 table for instance 3. So let's recreate the database with the updated schema. Let's try to do an insert. It worked. Let's try to insert in instance 2 and instance 3. If we select from dbo.person, which is the view, let me include the actual execution plan as well. If we do this, select star from dbo.person, it gave us records from instance 1, instance 2, and instance 3. Obviously, if we call them by themselves, so from person 1 we got 1, from person 2 we got instance 2, and from person 3 we got instance 3. So the view is actually working and consolidating the records together. However, the execution plan shows that we are querying all the three tables together. So we're using person 1, person 2, and person 3. Even when we use our criteria on the name, for example. So in this case, although we had no results, the execution plan shows that all the three partitions were actually invoked. Now, if we add the instance number in the predicate, so we're going to select star from person where instance equals 1 and first name like A. Although we don't have any results, the execution plan shows that it was only one table, person 1, that was queried. So that's the conclusion of the first demo. The third section of this presentation focuses on distributed partitioned views. First of all, let's start with a definition. What are distributed partitioned views? They are a form of horizontal partitioning, as we just did. However, each partition is distributed to its own server. These are also referred to as federated databases. We use distributed partitioned views when applications are unaware of such partitioning, cannot query multiple servers and need to access one data source. We use linked servers so that the partitioned view accesses partitions which are remote, and we can improve performance on linked servers by enabling a lazy schema validation option. This option ensures that the remote table schema is only validated on access. By default, distributed partitioned views for read-only access works everywhere. However, updatable views require the Enterprise Edition. If we only have Standard Edition and we want to make our distributed partition views updatable, we need to use the instead of trigger approach as we did during the demo. And here it is. This is the feature list for SQL Server 2019. Distributed partitioned views, yes, under the Enterprise column, and no for all the other additions. Distributed partition views have some requirements for the tables, for the columns, for the partitioning column. These rules, you can read them through here or access more details through the link below on the slide. Distributed partition views are updatable, so we can run insert statements, updates, and deletes based on these guidelines. So we need to abide with these rules. Let's have a demo. So for this example, for this demo, I've set up a number of servers. I have 4 servers running Enterprise Edition and 4 servers running Standard Edition. We're going to do the first example using Enterprise to see that we can make it work out of the box without using triggers. I'm going to create the partition tables on SQL Ent 1, 2, and 3 as instances, and then I'm going to create the distributed partition view on SQL Enterprise as the default instance. So let's start. Distributed tables. Okay, so I'm going to create a new database named distdb. I'm going to create this table on the 3 instances. So let me copy this code and I'm going to execute it against a server group. So it runs on all the 3 servers. So for now, I'm going to create a table named person with instance, person ID, first name, last name, but without a primary key, without a check constraint. And then I'm going to insert a record in each table. So let's run it. And here we have a record coming from instance 1 in SQL Ent 1, 3 from 3, 2 from 2. Now let's create the view. So I'm going to connect to the other instance, SQL Ent, which doesn't have any tables. So let's create a database on master distdb. So now we have a fresh database, distdb, no tables, and for now, no views. So the view that I'm creating now, dbo.person, is reading from 3 databases. We're using the fully qualified name for part name. It's the instance SQL Ent / SQL Ent1 .database distdb.schema dbo.table person union all with the equivalent from instance 2 and instance 3. And like that we got a record from each instance. However, if I try to insert a record, it gives an error. Union all view db.dbo.person is not updatable because a primary key was not found on table SQL ent1 this db.dbo person. So the first thing we need to do is recreate the tables using the primary key. So let's remove the comment that I did on the primary key. And I'm going to recreate by dropping and creating everything. Okay, so if I run the same insert statement again, now I got the same error, not updatable because a primary key was not found. But if I recreate the view and reinsert, now I got a different error. Union all view this dbo person is not updatable because a partitioning column was not found. So let's remove the comment. So let's include the check constraint. So on server 1 it's going to be instance 1, on server 2 it's going to be instance 2, and on server 3 it's going to be instance 3. Recreate. Let's recreate the view. Let's run the insert again, and now I got a different error. So basically this error, unable to start a nested transaction for OLEDB provider MS OLEDB SQL for linked server SQL and O1. A nested transaction was required because exact abort option was set to off. So first of all, I'm showing you here that I'm calling a linked server. However, if we go to server objects on SQL end, we can see that we have the 3 linked servers there. Now, in order to address this error, we just set exact abort on and retry to insert the statement. F5. Now I got another error. The attempted insert or update of the partitioned view failed because the value of the partitioning column does not belong to any of the partitions. This is because I'm trying to insert instance 0, which does not exist. If I try to insert instance 1, it works. So like this, if I do a select and include the actual execution plan, select star from person, now we're going to see the original 3 records, 1 per instance, plus the last one that we just inserted now. If we look at the execution plan, now we see that it's still calling the 3 sources, but now there's a distinction. It is a remote query. If we do select where instance equals 1, same as in the previous demo, the execution plan shows that it's accessing only that particular partition, but in this case it's a remote query. So let's select again, let's choose one of the persons. In this case the person ID was a GUID. I'm gonna change the first name of this GUID. If I select, we receive it with a different name. If I delete by first name and try to select again, wow, isn't there anymore. So like this, just by following basic rules of having a primary key and a check constraint plus the exact abort on to support and the nested transaction that it is running underlying the query, we are using updatable distributed partitioned views out of the box. So now the next example is to actually try to run this on a standard edition. So I'm going to use the same structure that we just did with the primary key and check constraint. I'm going to create it on the standard instances. So now I have one record on SQL std1, on std2, and std3. But if we look at the views, so I'm going to create a new database, this DB on it, on SQL std, which is the default instance, and this time the view is reading from SQL std1, 2, and 3. So it is the equivalent of what we did with the enterprise version. So select star from person. We got the 3 records. If we include the execution plan, still all 3 were queried. If we use a filter with the partitioning key, still filters and accesses only that partition. So till now it's exactly the same like enterprise for read only. But as soon as I try to do an insert, it gives an error when referencing tables on multiple servers. Views referencing tables on multiple servers are not updatable in the addition of SQL Server. So basically, we cannot do updatable distributed partition views out of the box on SQL Standard. So this is the same not just for inserts, but also for updates. Same error as well as for deletes. So exactly the same error. So now what I'm going to do, I'm going to create a trigger on this view, dbo.person, dbo.tr and tr person as a trigger. I'm going to use it instead of insert, delete, and update. I've split the trigger into 3 sections, one for inserts, one for updates, and one for deletes. I'm handling the inserts by doing an outer join, a left outer join between the inserted and deleted special tables. If there is no record in the deleted table, it means it is just an insert. So I'm inserting in instance 1 where the instance number is 1, and instance 2 when the instance is 2, and 3 where instance is 3. Then for the updates, I'm using an inner join between both special tables and the existing partition, because in this case, if there is a record in the inserted and there is a record in the deleted for instance 1, that means that the record exists and the command is an update. Same for instance 2, filtering ID2, and instance 3, filtering ID3. When it comes to the delete, I have a left outer between the base table person and inserted. So like this, we know there is no no record that got inserted, but an inner join with the deleted, because obviously there is a delete. That means there's no update, there's no insert, but it's just a delete. So filtering with instance ID 1 for instance 1, 2 for 2, 3 for 3. If we execute this trigger and then go and run the statements as before, so select it works, let's do an insert. We're going to insert a new record in instance 2. So let's prefix the first and last with a 2 so that we'll identify it. F5, it worked. Let's confirm with a select, and there it is. This is the record that got inserted through the trigger on a distributed partition view in a standard edition. If we take the ID of the record that we just created and change the name, it's going to work. And there it is. And if we do a delete by name, it works as well. And select doesn't get it. So like this, with an instead of trigger, we replicated the updatable views across distributed servers using standard edition. The only problem with this approach is that if we remove a server, a database, or we need to add a new one because we added a new partition, we need to come here and update the trigger. Obviously, the more partitions we have, the worse the trigger might perform. So this concludes the second demo. The last section that we have is database sharding. From a definition point of view, database sharding is a form of horizontal partitioning, in which partitions are distributed on commodity servers. SQL Server doesn't provide sharding natively, so database sharding needs to be handled at application level. From a database point of view, database sharding and distributed partition views would have the same partitions. The difference is that distributed partition views require a view that joins all the partitions together using linked servers, whilst that using database sharding, there is no such consolidation. Each partition is referred to as a shard when we're using database sharding. Like distributed partition views, sharding addresses the issue of having a single monolith database. However, it goes a step further in ensuring that there is no single entry point towards your database. With distributed partition views, we still had a view that joins all the partitions together, and as per best practice in the demo, this was in its own instance. However, database sharding allows applications to access shards that are geographically near them, thus improving network connectivity and reduce latency. Database sharding has its own problems. Queries that need to join multiple shards together cannot be done at database level. There are no views, there are no linked servers. Therefore, such consolidation needs to be done at application level. Also, referential integrity might be non-existing, because with shards we usually distribute transactional information. Referential tables would be in a centralized database somewhere else. We might be able to keep a copy of these referential tables across all the shards, but that would introduce another level of complexity to keep these tables synchronized across all shards. Another problem with sharding is the rebalancing issue. Rebalancing shards is required when you add a new shard. Let's say you had 4 shards and you are reaching storage space on all the shards. If you introduce a 5th shard without rebalancing data, you're going to have 4 shards which are full of data and an empty shard. Therefore, you might end up sending only traffic to the empty shard and creating a hot shard. Rebalancing means that we need to move data out from the existing shards and place it in the new shard so that all the shards end up with empty space to receive new insertions. Since with database sharding there is no single entry point to access the data of all partitions, the applications need to apply a database sharding strategy that will lead them to the data required. The lookup strategy creates a sharding map. Let's take the example of a multi-tenant application. One could say that each tenant has a shard. You would have a number of database servers storing multiple shards, i.e., having a database per tenant on each server, with some servers having multiple databases because they store multiple tenants. This map would know which tenant resides on which server. Then there's the range strategy, which groups data together by sequential information. So it is used when you want to get multiple sets of information together. The last strategy, the hash strategy, uses a hash to take a resource record ID, hash it, and based on that hash, place it in one of the shards randomly. So this makes sure that all the data coming through is properly distributed across all shards without actually keeping a map. So whenever you want to get information for an ID, you create a hash, and based on that hash, you would know under which shard the record is, and then access that record directly. So sharding is a bit more complex than database partitioned views, distributed partitioned views, because of this lack of single point of entry. So that's all for this session. If you have any queries and questions, do not hesitate to send me an email at roland@roland.net. Thank you.